Okay, in the next problem, a zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposited entries in a special box between noon and 8 p.m. That's t equals 0 and t equals 8. The number of entries in the box t hours after noon is modeled by a differentiable function e for t greater than or equal to 0, less than or equal to 8. Values of e of t in hundreds of entries at various times t are shown in the table above. So it's important to understand that this is kind of a cumulative. The e of t is a cumulative value of hundreds of entries in the box at a particular time t. It's not the entries that were added at time t, but it's the total entries in hundreds of entries at time t. So we want to use the data in the table to approximate the rate in hundreds of entries per hour at which entries were being deposited at times t equals 6. Well, since what we have is hundreds of entries, we actually have a quantity, and we want to find the rate at which the entries are being deposited at time t equals 6. We're going to use the values at 5 and 7. So we're going to say e prime at, not at 8, but at 6 is roughly equal to, we're going to have e of 7 minus e of 5 over 7 minus 5. And that turns out to be 21 minus 13 over 2. And so that is 4. And the units there would be hundreds of entries per hour. Okay, so that's part A. Part B, use a trapezoidal sum with 4 subintervals given by the table to approximate the value of 1/8 of integral 0 to 8 e of t dt. Then use correct units to explain the meaning of that. Well, this is obviously an average value of the e of t, and so if e of t is hundreds of entries, then the average would be hundreds of entries also over the time from 0 to 8. So we're going to use these 4 subintervals, and they all have different widths. We have 0 to 2, then 2 to 5, then 5 to 7, and 7 to 8. So we have h equals 2, h equals 3, h equals 2, and h equals 1. And remember, the formula for area of a trapezoid is h over 2 times the sum of the parallel bases. So we have the h's, and we're going to need 4 of these calculations. And let's see, the sum of the bases for the first subinterval will be 4, for the second subinterval will be 17, for the third subinterval will be 34, and for the fourth subinterval will be 44. And so we say 1/8 integral from 0 to 8 e of t dt is roughly 1/8, we can't forget that, and then it's going to be 2 over 2 times 4 plus 3 over 2 times 17, then 2 over 2 times 34 plus 1 over 2 times 44. So that's going to be 1/8, 4 for the first one, 25.5 for the second, 34 for the third, and 22 for the last. And this is a calculator problem, so we can go ahead and calculate that. So 4 plus 25.5 plus 34 plus 22 is 85.5. Divide that by 8. We end up with 10.688. So that would be 10.688 hundreds of entries over the time interval from 0 to 8. So that's the average number of hundreds of entries during that time interval. For part C, we're told that at 8 p.m. volunteers begin to process the entries, and they process the entries at a rate modeled by the function p, where p of t is t cubed minus 30t squared minus 298t minus 976 hundreds of entries per hour from 8 to 12. According to the model, how many entries have not yet been processed by midnight? So what we want to do is find the integral from 8 to 12. That will tell us how many have been. So we set up the function, and then I'll use fn int. I do vars y vars function y1 and integrate from 8 to 12, and I end up with 16. So we have to remember there were 2,300 entries at the time t equals 8. We subtract from that the 16, and we end up with 700 entries not yet processed.